name is Alexander Knopp, and this is Introduction to Mathematical Logic. In the previous video, we defined natural deduction. In this video, we are going to discuss the most important properties of this system. They're called soundness and completeness. And soundness said that if you can prove something, it's a tautology. Completeness, on the other hand, said that if you have a tautology, you can prove it. Let's start from the soundness. Formally, the soundness property is the following. If you have a formula phi, a propositional formula, then if there is a proof of phi, then phi is a tautology. The proof of this theorem is a bit too technical for this video, so we are going to illustrate it with an example with the hope that it's easier to follow. So example we are going to use is the law of excluded middle we proved in the previous video. The proof was like this. So what we are going to do is the following. We are going to replace every line of the proof by a propositional formula such that all of them are tautologies, and we'll finish with the tautology we wish to prove, and it will prove the theorem. So we start with an empty line because we don't have any assumptions, and the first actual line is an assumption that A or not A is not true. We rewrite it like this. So we say that under the assumption that A or not A is not true, we can derive the assumption itself. The next step is creating a new assumption. So we say that under assumption not A or not A, assumption A implies itself. Finally, we have the third step, and the third step is introduction of disjunction from the second step. So it's under the assumption that A or not A is not true, and assumption A, we know that A or not A should be true. Note that these two formulas are tautologies just because the assumption and the conclusion are the same. Here, we use the fact that this is a tautology, and we replace conclusion by the conclusion that the conclusion is true or something else. And in other words, this is still a tautology. After that, we have the first step. We concluded that under the assumption that A or not A is false and A is true, we get a contradiction. And we rewrite it like this. Under the assumption A or not A is not true, and under the assumption A, we get a contradiction. Note that this is also a tautology because the third one was a tautology. You had an assumption that A or not A is false, and you got a conclusion that A or not A. In other words, it's a contradiction because they cannot be correct at the same time, so we get a contradiction. Now we got rid of A, and we derive that under the assumption that A or not A is not true, we get not A. Now that this is a tautology because here we have a conclusion that A implies a contradiction. In other words, not A is true. Now we have a sixth step, and it's saying that under the assumption that A or not A is not true, we can prove A or not A. And this is a tautology because this is a tautology, and we just replace the conclusion by A or this conclusion. Finally, the seventh step is that under the assumption that A or not A is false, we get a contradiction. And this is a tautology because this is a tautology, and we have assumption and the conclusion, and they're opposites, so we get a contradiction together. Finally, the last step is A or not A, and this is a tautology just because the seventh step said that if you have an assumption, you get a contradiction. So the assumption was wrong, And in other words, A or not A is a tautology. And it finishes the proof. The next property we are going to discuss is completeness. And formally it says like this: if you have a propositional formula and this formula is a tautology, then there is a proof of this formula. This theorem is actually even more involved than the previous one, so we again illustrate it with an example. Let's try to prove that negation of A or B implies not A or and not B. In other words, it's a De Morgan's law. The idea of the proof is the following: we are going to simulate the proof by a truth table. In order to do this, on the first two steps, we derive that A or not A and B or not B. Note that these are actual derivations. We need to make several steps in order to do this, but imagine that we already have them. The next step is to consider cases if A is true or not A is true. Inside of both of these cases, you need to consider the cases if B is true or not B is true. Let's consider the first out of these four cases, when A is true and B is true. We need to prove that in this case, this implication is true. In order to do this, let's assume that not A or B. After that, we may notice that this is actually false under the assumption that A and B are true, because A or B in this case is true and negation is false. So we can derive the contradiction, and after that we can derive this. So we notice that we have A and B, so we can derive A or B using the introduction of disjunction. Note that it contradicts to the assumption, so we can derive a contradiction. And from the contradiction we can derive everything, including not A and not B. And since with this assumption we can derive these, we can derive the implication. So we prove that if A and B are assumed, we can derive this. Now let's consider the case when A is true and not B is true. In this case, again, we made the assumption that not A or B. And we know A, so we can derive A or B. And remember that since A is true, the assumption is false. So we need to get a contradiction. But A or B contradicts to this assumption, so we get a contradiction. And we can derive everything, including the conjunction of not A and not B. In other words, we can prove the implication. And in other words, if A is true, using B or not B, we can derive everything we want. So we prove that if A is assumed and B is assumed, we can derive these. We also prove that if A assumed and not B is assumed, we also can derive this. Using the fact that A or not A should be true, we can derive this under the assumption A. We consider the case when A is true. Now we need to consider the case when not A is true. And again, we need to consider two cases, for B and not B. First, the case when B is true. So we know that not A is true and B is true. Again, let's assume this. Note that B contradicts to this, because A or B is true. We can derive it from B using introduction of the disjunction. And this together gives a contradiction. And we can derive everything from the contradiction, including not A and not B. So using introduction of the implication, we can derive from this implication. And the last case we need to consider is when not A is true and not B is true. Note that in this case we again need to assume this, and this time not A and not B are not contradicting this, and we can derive this just by the law that if you derive not A and not B, you can derive their conjunction. And in other words, with this assumption we can derive this, and as a result we can derive the implication. And since in both cases B and not B we can derive this implication, we can derive the implication without any assumption about B. And we also can derive this implication in the case A, and in the case not A. So in other words, we can derive the implication without any assumption at all. And this finishes the proof. In this video, we finished with propositional logic by discussion of soundness and completeness. In the next part, we are going to discuss a more complicated model, which is called predicate logic. If you have any question, ask them in the comments. See you later.